folks, welcome back. So we want to continue our conversation about finding limits numerically and graphically. And I left off by saying there are really three ways to calculate a limit. You can calculate it numerically, which is use a table, get closer and closer numerically by plugging in values closer and closer to your C value into the function and see what your answers are. Graphically, you take a look at a graph. Remember, the function does not have to be defined at that point. There could be a hole in the graph at that point, but you'd actually visualize if the hole were filled in, what might the answer be? I don't want to say that's the quick solution for all of them, but that might apply. And then analytically, we haven't learned how yet, but in the end, that's going to be the easier, quicker way to find limits is using properties that will be discussed in section 1.3. But we need to continue our conversation now by discussing numerically and graphically. So let's move on to another example. So right here, you will notice that absolute values are very common in calculus. They make some very interesting examples. So here's what I want to do. We want to plug in numbers closer and closer to -1. Now remember, this is numerically, which means we're going to just use a table, not a t-table, but a table. You could call it a t-table if you like. And plug in numbers closer and closer to -1. What would you like to pick? I've got lots of spaces here, but all of them are not required. Now, -2 is somewhat close to -1. You could try -1.5 or -1.1. Now we're getting close, right? -1.01 or -1.001. And might be overkill, but we could do that. And that's definitely getting super close to -1, but it's on the left, so you're talking about a little smaller than -1. And then on the right, well, 0 is bigger than -1, but -0.5 is a little closer, and then -0.9 is even closer, right? And -0.99 is even closer than that, and -0.999, you get the point, and -0.9999 is super close to -1. So we're going to take these values and plug it into the function and see what we get. Okay, so I take -2 and plug it in. Oh, by the way, notice the notation. It's the first time I've written the notation. We're going to take the limit as x approaches, that's the way you would read that, as x approaches, if I can spell that right, -1. Now that's from the right and the left, so if you ever see that, that means you're going to get closer to -1 on both sides, and you must check both sides, okay? So we're going to do that. So if I plug in, say, -2, you would have the absolute value of -2 plus 1 divided by -2 plus 1. Okay, what's the absolute value of -2 plus 1? First of all, what's -2 plus 1? Well, we know that's -1, but it's still in an absolute value divided by -1. Okay, now the absolute value of -1 is +1 divided by -1, which is -1. And then I try it again with -1.5. So I have the absolute value of -1.5 plus 1 divided by -1.5 plus 1. Well, in the numerator, -1.5 plus 1 is -0.5, still in the absolute value, divided by, well, -1.5 plus 1 is -0.5. Now in the numerator, the absolute value makes this positive 0.5, but it stays negative in the denominator, and I get -1. Okay, let's try this again. Do you think we need to? We got -1.1. Let me write this properly. You just keep going. There we go. -1.1 plus 1 in absolute value divided by -1.1 plus 1, and not in the absolute value. So notice every single time we're going to get the same result in the numerator and denominator. Do you agree? Every time. Because it's the same thing, x plus 1. But in the numerator, it's going to turn positive. So you're going to have -0.1, but it's going to turn into positive 0.1. And the denominator is going to stay whatever it is, which in this case is -0.1. And then I divide that, and I'm going to get -1. Now I promise you, pause it if you don't believe me, but I promise you, you're going to get -1 for all of those. Okay? Because you're going to get the same value in the top and the bottom. If you plug in a number smaller than -1, like -1.00001, you're going to get a negative in the denominator, but you're going to always get a positive in the numerator, which is going to give you -1. Now let's look at the other side. Okay, so I'm going to erase down here while you're still thinking about that. See if you can prove me wrong. That's always what I want you to do, is see if you can prove me wrong. That means you're thinking all the way around it. Okay, so the next thing I'm going to do is plug in 0. Okay, kind of far away from -1, we're going to plug in 0. I'm going to do it in a different color too. So I have the absolute value of 0 plus 1 divided by 0 plus 1. Okay, well in the numerator, that's the absolute value of +1 divided by the denominator is just +1. So on top I get 1 because the absolute value of +1 is still 1 divided by 1, which is 1. Okay? Alright, sort of like the last one, but not the same. -0.5 plus 1 divided by -0.5 plus 1. Now in the numerator, -0.5 plus 1 is +0.5, still an absolute value, divided by -0.51 is +0.5, not an absolute value. So that's 0.5 divided by 0.5, which is 1. Okay, now, once again, I'm going to get the same value in the numerator and denominator. But the top is always going to turn positive, right, because of the absolute value symbols there. The denominator, what's it going to be every time if we're bigger than -1? Okay, then you're going to be positive. All along here, it's going to be a positive number in the denominator. It's also going to be a positive number in the numerator, right, because you're doing absolute value. And they're always going to be the same value. And if you don't believe me, just plug in all those numbers separately. You'll see the pattern. But I promise you, all of those are going to be +1. Now, what doesn't matter is what happens at -1. Matter of fact, what does happen at -1? If you plug in -1, you get 0 over 0. Remember, we can't do that. That's undefined. So I can't even plug in the C value. Now, here's the deal. If the limit on the left side does not match the limit on the right side, this limit does not exist. If you'll notice, the other problems that we did in the last video, when we were doing these numerically, it was approaching the same number on both sides. It has to be, or the limit does not exist. Now, the quick way to write does not exist is DNE. That is an acceptable answer. That is the correct answer. Okay? So, not every function has a limit at every value. So, you've got to keep that in mind. So, this is the first way a function cannot have a limit, is you get different answers on the left and the right. Now, let's check this next problem out. So again, I'm asking you to find the limit as x approaches 0. Notice I have 0 right in the middle of my table right here. Numerically, so that invites a table. Hey, if it says find the limit numerically and it doesn't give you a table, you got to build one. Okay, it's still asking you to do the same thing, even if a table is not offered up for you. I'm just doing that in my notes because it makes it easy. Now, my question is, can we just plug 0 in? Well, let's try it out. It would give me 4 over 0 squared, which is undefined. I can't do that, right? So, even if I could do it, we still need to do this numerically, which means get closer and closer to 0 from both sides. So a number less than 0 might be -1, or we could try -0.5, or we could try -0.1. Remember, the goal is to get very close to 0. That's super close. That might not be necessary. And we need to do it from the right, too. Like, 1's pretty close to 0, but I can get closer by doing 0.5, or 0.0, or 0.1, or 0.01, or 0.001. You see where I'm going with this? 0.0001. Okay? So, smaller than 0 on the left, bigger than 0 on the right, getting closer and closer. Now, this is some number crunching here. When I plug in the first one, -1, that'd be 4 over -1 squared. That we can do in our heads. That's just 4. But now, once I move on to the decimal, we may want to save some time and plug that in our calculator. Okay, so I'm going to pause it, plug in the left side, we'll discuss, and then we'll come back and plug in the right side. Whoa, look at those numbers. Did that happen to you? Okay, so when I plugged in negative 0.5, I got 16. That seemed pretty reasonable. Then I plugged in negative 0.1. Now think about what's happening. You've got a 4 on the top every time. But when you square 0.01 or 0.1, okay, you get, so type it in just so you see, 0.1 squared, you get 0.01. Then you take 4 divided by 0.01, and that's going to give you 400. And it's going to work all the way across to the point where when I plugged in negative 0.0001, I got 400 million. Okay, so what is that getting closer to? You see the 4s and you think there's a pattern, but that's going to infinity. Am I right? It's just getting bigger and bigger and bigger and bigger. It's not getting closer and closer to anything. Now what's going to happen on the other side? Well, think about what's going on. You know, we're taking the same values on the other side and squaring it, so you're going to get exactly the same answers, aren't you? When you plug in 1, you're going to get 4, just like when you plugged in negative 1. Or when you plug in 0.5 positive, you're going to get the same thing as when you plugged in negative, because you're squaring the numbers. So this 0.0001 is going to be 400 million again. So this is also going to plus infinity. Now, what does that mean about the limit? That means the limit, once again, does not exist. Okay, so if you ever get a limit that either goes to positive infinity, which means it's getting bigger and bigger and bigger and bigger, or negative infinity, which means it's getting smaller and smaller and smaller and smaller, not decimal-wise, like negative 400 million, you know what I mean? Then you have a limit that does not exist. Now, the infinity's extra important. It tells you how it doesn't exist, but I want you to realize it does not exist. Now, I want to go back real quick and discuss an earlier problem. Okay, remember this one right here, the absolute value? What I meant to do was show you a quick graph of this, because they didn't ask us about the graph, but I want you to see what this looks like graphically as well. This, if I were to graph this, and I'm not going to take a whole lot of time and show you how to do it, think about this like a t-table. Okay, so at negative 1, this is completely undefined. Okay, but anything bigger than negative 1, like over here, my answer is just a constant 1. Okay, so this is 1. It looks like this, all the way to the right. Now, it's an open circle right there because it's not defined at negative 1. On the other hand, to the left, my answer is negative 1. Again, it's not defined at negative 1. That's the graph right there. It's piecewise because it's in pieces. But notice as you approach from the left, the answer is negative 1. But as you approach from the right, the answers are all up here at positive 1. And that's what that looks like. So you could see the left and the right don't match. On the other hand, this problem, if I were to graph it just really fast, first of all, let's get some ink. Okay, here we go. There's our XY axis. I know I have a vertical asymptote at x equals 0, right? Because it's undefined at x equals 0. Basically, when you have it squared, everything turns positive. So you're looking at a graph that looks similar to this, okay? So notice here's 0 right in the middle. As you approach, let's go with red. As you approach 0, from the left, look, our answers are getting larger and larger and larger to the point where you go up to 400 million and even higher. As you approach 0 from the right, that's this side of the table, again, our answers get larger and larger and larger. Therefore, there is no limit value. Now, here's an interesting problem, and don't clam up on me. You took trig before this class for a reason, so we do have to deal with a decent amount of trigonometry in a calculus class, and this will be our first one. We want to take the limit as x goes to 0 of the cosine of 1 over x. Now, I got 0 right in the middle of my table. They want us to do this numerically, hence the table. But if I calculate the cosine of 1 over 0, I got a problem, right? Because just this alone is undefined. I'm not allowed to do that. So what I have to do is plug in values closer and closer to 0. Okay? Now, one thing we could do, you know, in trigonometry, we're used to thinking about angles in radian mode that we plug into a trig function. So for example, we could plug in something, let's think about something bigger than 0, like 1 over pi. I know that seems weird, but that is bigger than 0, right? Because it's positive. And it would be easy to plug in here, right? Because you would calculate cosine of 1 over pi, which would be the cosine of pi. Anybody remember what the cosine of pi is? Remember, pi is the x value on the unit circle. The cosine is the x value on the unit circle. Pi lives right over here. The x value right over there is -1. You remember all this? Now, what's closer to 0 than 1 over pi? Well, 1 over 2 pi is closer, right? Then you do the cosine of 1 over 2 pi, which will give you the cosine of 2 pi, because remember, you have to flip and multiply. You flip and multiply. What's the cosine of 2 pi? Remember, 2 pi is all the way around the circle. The x value on the unit circle all the way around is 1. Okay, what's even closer than 1 over 2 pi? 1 over 3 pi, right? So then we would calculate, I'm going to move over here, cosine of 1 over 3 pi. Got to flip, so that's the same as saying the cosine of 3 pi. What's the cosine of 3 pi? It's the same thing as the cosine of pi, which is -1. And then you calculate 1 over 4 pi, because we're getting closer and closer to 0. You know what that's going to be? 1. And it's going to alternate like that. And you could do negative values as well. Like you could do -1 over pi, -1 over 2 pi, -1 over 3 pi, -1 over 4 pi, -1 over 5 pi, -1 over 6 pi. If you keep doing that, you get closer and closer to 0. Let's run the numbers. We won't do a bunch. Let's just do cosine of 1 over -1 over pi. Got to flip that, right? That's the cosine of, when I flip and multiply, that gives me -pi. What does negative mean? It means you go backwards around the circle. So I go this way, there's -pi. The x value, because cosine is the x value on the unit circle, is -1. That's our answer. And then when I go -2 pi, it's all the way around back here, and I get +1. What's going to happen? Again, these are going to alternate. Okay, just like on this other side, they continue to alternate. Now, what does that mean? This goes from -1 to +1, -1 to +1, -1 to +1, as we get closer and closer to 0, that means the limit does not exist. It's oscillating is what that's called. It's flipping back and forth, back and forth, back and forth. So this is the term I'm saying. Okay, oscillating. Just got tired of writing it. There you go, oscillating. Let me show you a graph of this, and it's pretty wild looking. Boom, there it is. Okay, so here's one of those -1 values down here. Then there's one of those +1 values, and then -1, +1, -1, +1. See what it does? And you can't see it because it looks like this solid area, but all this is going up and down, 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 and continues that way forever, all the way as it approaches 0. And obviously it's doing it on the other side as well. So there's oscillates written properly. Okay, and what does that mean? It means the limit does not exist. If the graph bounces back and forth to the same number. Now, there is a graph, you'll see this in the future, that does oscillate, but it gets smaller and smaller each time it oscillates. That's not the same thing. This is going from -1 to 1, -1 to 1, over and over and over again. Therefore, the limit does not exist. I know, it's the weird examples. So let's recap a little bit about this non-existing limits, or the DNEs, does not exist. Okay, one situation is the limit from the right and the left does not match, or the limit from the right does not equal the limit from the left. Remember, we had that with that piecewise function. Not at all telling you that every piecewise function, that's what's going on. That's what's going on in this particular piecewise function. The left limit is -1, the right limit is +1, they don't match. Okay, a second way a limit does not exist is it either goes to plus or minus infinity. When you have rational functions, in other words, these polynomial fraction functions, it's a possibility your limit may not exist because it either goes to plus infinity or minus infinity. Now careful, it would be where a vertical asymptote exists, and it would have to be the limit as x goes to 0. For example, if I asked you to instead find the limit as x goes to, say, 5, it would have an answer. But if the c value right here is the same as a vertical asymptote, then you're going to get plus or minus infinity for your answer. And a third way that a limit cannot exist is the function oscillates between two fixed values. Notice it says fixed values. In our particular problem, it went from -1 to +1, -1 to +1, -1 to +1, over and over again. Okay, so let's do a homework problem. Again, stolen right out of homework examples. They give us a graph. It's tiny. You might want to put your glasses on or zoom or something. Okay, tiny down here at the bottom. They give us a graph, and they want us to find quite a few things. A, they just want you to evaluate f of -2. Now remember, when you see this notation, this is your x value on the inside. So this is your x value. They want us to find the y value. So I go over to -2, and look, there's a vertical asymptote right there. So f of -2 does not exist. There is no function value for -2. Then they want us to find the limit as x goes to -2. So as we get closer and closer to -2 on the left side, it goes to negative infinity. So you check that out. Okay, so watch this. As I sneak in over here and I get closer and closer to -2 from the left, what are my y values doing? They're going down here to negative infinity. Okay, on the other hand, as I get closer and closer to -2 from the right, what are my y values doing? They're going up here to plus infinity. Either way, that means the limit does not exist. So you either get plus infinity or you get minus infinity. No matter what, that means the limit does not exist. Okay? C, they want us to calculate or find f of 0. Let me do a little bit of erasing here. Okay? So f of 0, so here's 0, right? I go to my graph, and there's a hole. So f of 0, once again, does not exist because there's a hole in the graph at 0. Oh, wait, back up. Did I do that too quickly? Look, let's look again. I did, I erased it. Look, if I go up higher, f of 0 does exist. The answer is 4. That's me not paying attention to the whole graph, just looking at this little piece. But look, up here it's defined at 4. But on the other hand, if we take the limit as x goes to 0, that means we need to look at what's happening from the left, and we need to look at what's happening from the right. So from the left, as I get closer and closer and closer to 0, my answer is up here at maybe 1, where the hole is. Okay? From the right, as I get closer and closer to 0, my graph is going up here, is going to 4. But here's the problem. The left and the right don't match. So the answer here is it does not exist. And the reason is the left does not equal the right. See what I mean? The left side is down here where the open circle is. It may be 1. The right side, coming from this way, is up here at 4. Okay? You have to go back and look at this in detail, but I'll make sure you're comfortable with this. F of 2. So first of all, where's 2? There's 2 right there. Now the limit from the left, we're getting closer and closer and closer to the open circle, right? Oh, first of all, f of 2. I'm not finding a limit. I'm just finding f of 2. F of 2 doesn't exist. There's a hole in the graph. Okay? But as you approach from the left, which I was doing in yellow every time, our graph is getting closer and closer to 1, it looks like. As we approach from the right, our graph is getting closer and closer to the same value. You see what I mean? So that limit does exist, and the answer is 1. I'm going to say it's 1. It looks like it's about 1. Oh, no. It's about a half, isn't it? Because there's 1 right there, and if I go and match the graph, I'm going to say it's 1/2. It's so tiny. Let's say it's 1/2. Okay. Next, we're looking at f of 4. Again, these are the weird examples. So here's 4 right here. The function value at 4 is that dot, and it is sitting over here at, I'm assured that's 2. All right, but now let's look at the limit. The limit is a different thing. It doesn't matter what happens at 4, what happens as you approach 4. So look, as we get closer and closer to 4 from the left, what's the graph doing? It's going up to plus infinity. So that's a plus infinity up there. Now on the other hand, as we get closer and closer to 4 from the right, what's the graph doing? It's also going up there to plus infinity. Now it doesn't matter if one was plus infinity, one was minus, it doesn't matter. That means the limit does not exist. So it's weird. Sometimes the function value can exist and the limit can not exist. Sometimes the function value cannot exist and the limit exists. Or sometimes, like in A and B, neither one of them exist. So go back and revisit this problem when you're stuck, possibly in the homework, thinking about limits that don't exist. Check out this problem. Love these. Love these. This is a thinking problem right here. Not only that, there's unique answers. So it doesn't mean that if your problem is different than your neighbor's problem that you've done it wrong. You could have both done this properly or correctly, but get different functions. So stop for a minute, pause it if you have to, see if you can draw a function that meets all 4 of these requirements. So f of -2 is 0, f of +2 is 0, the limit as x goes to -2 is 0, and the limit as x goes to +2 does not exist. Did you get it? Remember, you have to pause it. I'm not asking you to do it that quickly. Okay, here we go. Let's do this. Let's think through this together. So first of all, f of -2 is 0. So I go over to -2, and my function value is 0. So I'm going to do a big old dot right there at -2, 0, because that's what it tells me is true. F of +2 is also 0. So I go over to +2, that's my x value. My answer is the f of value or the y value, and it's 0. Now it says the limit as x goes to -2 of my function is 0. So the limit, that means the limit from the left and the limit from the right at -2 match. Now this is where it could differ for everybody. Okay, so it could look, you know, like this, right? Because the limit from the left, as we get closer and closer to -2 from the left, my answer is 0. As we get closer and closer to -2 from the right, my answer is 0. So that would work. But on the other hand, the limit as x goes to +2 doesn't exist. So I could come back up and meet the graph. Then on the other side, could have some situation like this. See, the limit and from the left and the right don't match. F of 2 is still 0. The limit as you go to 2 from the left is 0, but the limit as you go to 2 from the right side would be up here at 4. Okay, again, we all may draw different graphs, yet we could all do this correctly because it meets these 4 conditions. Those are fun examples to me. I think they're worth trying and make you think about what's really going on. So this is the last example I want to take a look at in this video, and then there'll be a third part to our notes for finding limits numerically and graphically, and that'll be the definition of a limit. You'll love that section. Okay, so here we go. Last problem. A little bit of trig for you. It's a piecewise function. So we've got 3 separate pieces. The good news is I gave you the function values and I gave you the graph. So I'm not asking you to graph it. I just gave it to you. It says that sine of x is our function when x is less than 0. So you're talking about this side, that's the red one, if you're seeing in color right now. So this is a regular sine graph, but it says for x is less than 0. So the red goes all the way up to 0, but doesn't include 0. Now, between 0 and pi, so notice 0. Now, what is pi? Y'all remember pi is about 3.14 rounded. So this is the blue graph. Between 0 and about 3.14, so about here, we have 1 minus the cosine of x. Okay? And then my third piece is in green. When x is bigger than pi, we have cosine of x. So just slightly bigger than pi, pi not included, then we have the green graph, which is cosine of x. Okay? Now, you didn't have to answer this question. Well, you kind of have to be given both. I mean, it asks what c values on this graph where the limit exists. I think it's easier to ask yourself, where does the limit not exist? Because there is one place that the limit does not exist. Where is that? That's right here where the graph breaks up. There is no limit when a graph splits up like that and the left side and the right side don't match. Now, the reason you need this is because when I look at it here, it looks kind of like it's at 3, doesn't it? But I do notice the blue goes a little past the 3 and the green doesn't go quite to the 3, so I know something shady going on there. So I couldn't look at just the graph and necessarily tell. But when you look here, you see it's defined all the way to pi, and there it splits up at pi. So that means this place where it splits up is pi. So the limit does not exist at pi. At x equals pi. That's a given that it's an x equals value, but to say this correctly, let's say x equals pi. Because from the left, notice my answer is at 2. Right there at pi, it's up here at 2. But if I'm coming from the right side, it is down here at -1, it looks like. Okay? We didn't have to say what those values are. We just know the limit from the left and the limit from the right don't match. If it helps, as I'm going to pi from the left, my graph is going up here. As I'm going to pi from the right, my graph goes down here. And clearly, those don't run together and turn into a nice green color. Okay? So how would I answer this? It does not exist at x equals pi, but that's not what it asks. It asks where it exists. I would say everywhere but x is equal to pi. So where does the limit exist? Identify the c values. All c values but x equals to pi. All right, that wraps up this video. And remember,